Dear student, today my lecture will be on conduction in semiconductors. So I will send later on the content of the lecture today also to you. Here I will try to just make it clear that how conduction is going on in semiconductors. So this is one just a lecture session here. First of all, today under this section I'll cover the subsections carrier drift, carrier mobility, saturated drift velocity, mobility variation with temperature, a derivation of Ohm's law, drift current equations, and finally the formation of band, semiconductor band with an electric field present there. So first see about carrier drift, how it happens. Basically, if we talk about the conduction process in semiconductor, two carriers are responsible for that. One is electron and other is holes. And the force acting on the carrier is given by this equation F equal to QE, where F is the force acting on the carrier, Q is the charge, E is the electric field, and obviously the drift current is given by this equation NQVDA, where N is the charge carrier concentration, that is the number of charges per unit volume, Q is the charge of the electron, and Vd is the drift velocity, A is area. So these are the two equations by which the conduction of electricity occurs in semiconductors. Now comes next carrier mobility. Generally it is given by this equation. The drift velocity is proportional to electric field A, so mu is the constant of proportionality, which is known as mobility of charge carrier. And you can see the dimension of mobility is like this. And basically what does it mean? What is the physical interpretation of mu or mobility? It is a measure how easily charge carrier can move under the influence of electric field. So mu determines how mobile the charge carriers are. Next, we go to N-type semiconductors, silicon. So you can see here one diagram, schematic diagram. A voltage V is applied along two ends of the semiconductor piece, and quite obvious you can understand here. V is the potential, L is the length of the piece, and electric field is directed from plus side to minus side. Electron movement opposite to the electric field denoted by red colored line, and current flow along this direction. And if we talk about the P-type silicon, there the major carrier is hole, the same as before, only the difference is that here hole movement along the electric field. So these are the two types of carriers take part in the conduction process in semiconductor. Now carrier mobility, two type of presentation is here. One is macroscopic understanding and other is microscopic understanding. So just in the previous slide I have shown that electric field is proportional to the drift velocity. So the constant of proportionality, that is Vd by E, is the macroscopic understanding of carrier mobility. And if we go microscopically, later on we will derive this expression also, the mobility can be given by this relation where Q is the charge, tau is the relaxation time, and m is the equivalent mass. If it is n-type semiconductor, then this m will be me, that is equivalent mass of electron. If it is p-type semiconductor, then m will be whole equivalent mass. So this is the two aspect of mobility if you see in the view of macroscopic point of view and in view of microscopic point of view. So the mobility in semiconductor is given by that equation, but it has two components. One mobility contribution comes from lattice interaction and other component comes from impurity interaction component. Means that when we talk about the semiconductor with doping, then two parts will come in the mobility. One is lattice interaction component and other is impurity interaction component. Then the thermal velocity, assume that crystal is at thermodynamic equilibrium condition, there is no field, that means. Then what will be the energy of electron at a finite temperature? That can be given by this equation, because electron have the thermal energy half kT per degree of freedom. Since 3D, so total energy of electron will be given by 3 by 2 kT, which is equal to half mv square, where Vth is the thermal velocity of electron. So one can see that thermal velocity is proportional to the square root of temperature. Also thermal velocity is proportional to the 1 upon square root of equivalent mass. But what happens if some current is given to the semiconductor? Then we will come later. Here one example is given. Just later you can go through the slide and try to understand based on this problem, and then you quantitatively you can understand the meaning of thermal velocity, also drift velocity. There is one example given here, right? Then microscopic understanding of mobility. Just I told you before that how long a carrier can move in time before collision. That moment mobility play an important role. Tau is the relaxation time, which is basically average time taken between collision. The question is that how far it can go before collision is given by this distance, which is known as mean free path or average distance taken between collisions. So in that case the drift velocity can be given by this equation. It is very simple, that we have considered the Newtonian mechanics, obviously taking mass as the equivalent mass, not the absolute mass, actual mass. So it is simple Newtonian equation. The drift velocity is given by F by m into tau, and then if we put the value of just force here, QE force, then it comes down the expression for drift velocity as mu e, where mu e is given by this relation here, Q tau by m. So this was mentioned before, that mobility microscopically can be given by this relation, product of charge and relaxation time by equivalent mass. So this is microscopical point of view for the understanding of mobility. Here is another example given here. For example, for a piece of n-type silicon, the different parameters given. For example, the effective equivalent mass for electron is 1.18 m naught, where m naught is rest mass of electron, and equivalent mass of hole is given 0.59 m naught, where m naught is the rest mass of electron. And mu is given here, that is electronic mobility 0.15 meter square per volt second, and that for the hole is given by this value. So in that case, there is an example here. What will be the relaxation time for electron and also hole? So if we see the figure, it is for electron mobility, the relaxation time is of the order of 10 to the minus 12 seconds, where for hole the relaxation time is less, of the order of 10 to the minus 13. It means that thermal velocity you can see for electron is 1.08 and for hole it is 1.052, almost equal. So if we consider this data, then you can see that electronic free path is 10 to the minus 7 meter order. For hole it is 10 to the minus 8 meter. That means for hole the free path is less. So relaxation time also for hole is less. So this is one example. From here you can understand microscopically the mobility of two carriers in semiconductors. Then there is a relation here given. The variation of drift velocity with the electric field. So you can see that at a lower range of electric field, the drift velocity is almost linearly varying with electric field, but when you go higher range of electric field, some time will come when it get almost saturated. And one thing here you can see here also, for electron the drift velocity is more, for hole drift velocity is less. So that means that electron move fast than holes in the semiconductor. Here the saturated drift velocity is given here. What just I told here is mentioned here. Then we go next slide. What is the variation of mobility with temperature? If we see at higher temperature zone, then mobility is decreasing with temperature. But if we see the lower temperature zone, mobility is increasing with temperature. So the effective mobility of charge carrier, if it is mu t, can be given by this relation, where mu L contribution comes from lattice mobility part and mu y, this contribution comes from the doped ionization part. So this is the variation of the log mu versus ln t. Then you can see one peak is here. So this is the variation of mobility with temperature. Then we go the two components, that is component from lattice. This mobility is basically proportional to T to the minus 3 by 2. So if temperature increases, then you can see it is decreasing at higher temperature. So this is basically T to the power minus 1.5 power law. So carriers are more likely scattered by the lattice atoms. Here it is understood. And if we see the other part which comes from ionized impurity part, it is directly proportional to the temperature 3 by 2 power. So these two parts take part in the mobility of charge carrier in semiconductor. So this is the variation of mobility with temperature, and also explained earlier with also electric field in semiconductor. Now next comes that based on this understanding we can derive the expression for Ohm's law also. If you can see the slide later on, you can understand everything here given. The deep current given by this equation, where N is the carrier concentration, Q charge, Vd is deep velocity, A is area, and Vd is given by mu E, where mu is the mobility. Then current density given by this equation, mu is given by this equation. The all expressions are given here. These are some relations. It is important if you go to solve some numerical problem. These are important also. If you go through the slide, you can understand also everything has been discussed already. Only here, for the sake of your just understanding, I just summarize the all relations here. Now the Ohm's law derivation you can see here. The current density along x direction given by sigma E, and where J is given by Ix by A, and sigma and electric field E equal to B by L. It is quite understandable because electric field is voltage by distance, and then if we put here B by L and sigma conductivity is 1 by rho, then current is coming V A rho L, or simply V by R. So this is nothing but Ohm's law. So from the basic principle we can obtain the Ohm's law also in this form. Then these are the drift current equation in case of semiconductor. The same thing as before, here very categorically written for the N-type semiconductor, where the electrons are major contributor for the conduction of current, and in P-type semiconductor where holes are the responsible for the conduction of current. These are relations. Another thing is there suffix given here N for electron and P for hole. And total current density will be given by this. Current density comes from electron and current density comes from hole. So as a whole, the current density, intrinsic current density in semiconductor given by this equation. If it is intrinsic semiconductor, then N equal to P equal to Ni, where N is the number of electrons per unit volume, P is the number of holes per unit volume, which is equal to intrinsic semiconductor Ni. So this is given by this equation. So this is the equation for deep current density equation for semiconductor, and here if we take the N-type semiconductor, then that small n can be substituted by the donor concentration in N-type semiconductor by Nd. Similarly for P-type, the same thing will be replaced for the P, the whole concentration by the number of acceptor concentration Na. So we get this equation, right? So now question is that why resistivity of metal increases with temperature and why resistivity of semiconductor decreases with temperature, with increasing temperature. So this can be just find from here. If you see this relation, then you can get the answer why it is so. But physical interpretation, I must say one thing, that if temperature increases, then in conductor the thermal collision will increase more, and in semiconductor also collision will increase, but at the same time the generation of hole and electron pair will be more. So it will it will just override the effect of thermal collision. This is the reason, due to the more generation of pair of electron holes, it will be dominating over the thermal collision, and this is the reason why in case of semiconductor for the increasing temperature the conductivity will increase. But in case of conductor there is no question for the generation of whole electron pair generation. So in that case the dominating will be the thermal collision, which will decrease the conductivity of conductor, or just alternatively you can say the resistivity will increase with temperature increase. Next will come the energy band diagram in semiconductor. So it is understandable, you know this one, that in semiconductor EC is the lower edge of the conduction band, EV is the upper edge of the valence band, and in between this the undocked semiconductor energy level is here, EI. So when we take say n-type semiconductor, then generally energy level of donor atom will lie with this red dotted line, and the Fermi energy level will lie between EC and EI. So you see that the electrons in the donor energy level is very easy to shift from donor energy level to EC, crossing this Fermi energy level. So in this process, what happened actually, the electrons in donor atoms take parts as the major carrier, transmitting from the donor energy level to EC. This is the reason in n-type semiconductor electrons are major carriers for conduction of current. Then what will happen for p-type semiconductor? Here something different. The Fermi energy level will lie between the acceptor energy level EI and EV, the upper edge of valence band. So the electrons in valence band very easy to shift from valence energy band to acceptor energy level, no need to go to EC. So here is also transfer of electrons is going on from EV to EI, or we can say that holes are created here in EV, or in turn it can be said that holes are taking part as major carriers in p-type semiconductors. So this is the process of conduction in p-type semiconductor. So this is about the conduction in semiconductors, and next I will go another topic, that is Hall effect. Hall effect, what does it mean? What is it? Let's see first. Hall effect is that, so this is a piece of conductor or semiconductor.